Hi there, my name is Sophie. Thank you for the great presentations in the symposium so far, and I apologise I can't be there in person to present today. First up, I'd like to acknowledge the large number of co-authors and contributors that are involved in the large body of work I'll be presenting today. I want to thank them all for the opportunity to share this work with you. I'd like to share my appreciation as well for the contribution of and emphasis on traditional owners in this conference. I want to acknowledge that sovereignty was never ceded and that all research presented was conducted on sea country with full, free, prior informed consent. So there's been quite a few other presentations in the symposium so far referencing photogrammetry and related image processing and AI tools. So I hope you're all warmed up, you've enjoyed the talks, and make sure you keep a lookout for the recordings if you missed any and you're interested. So in this talk specifically, I want to provide a brief overview of photogrammetry's application in quantifying key reef metrics for understanding reef resilience and informing restoration. So photogrammetry refers to the use of photography to map and measure objects in the environment. And while terrestrial photogrammetry has been used since the 1800s, underwater photogrammetry has only really increased in the last 10 years. All photogrammetry, however, consists of a few key aspects, namely a camera rig, reference markers to scale and georeference the models, and of course the collected photos and benthic imagery. These images go together to create 3D reconstructions of the environment of interest or a digital twin. And when we talk about coral reefs in 4D, we're not exactly time traveling, but we are talking about time series 3D reef data. So the process of photogrammetry involves first divers or vessels collecting imagery continuously in a systematic pattern across the area of interest. These photos are then fed into a photogrammetry software such as AverageSoft Metashape, which uses structure from motion algorithms to build models. These models are constructed by first locating clusters of pixels from multiple photos and triangulating their position in 3D space to build what we call a point cloud. Triangles are then interpolated between these points to build a solid surface or mesh, forming the 3D model. Next, the photos are wrapped across the mesh to create a textured model as shown here. If we're assessing the change or comparing models through time, models from 2 time points are then lined up in 3D space through a process called co-registration. This is done before the final outputs, 3D models on 2D photo collages called orthomosaics can be exported. These outputs are then analysed using a range of methods to extract a diverse array of information. So this is an example of 2 3D models that are captured at different spatial scales and could be used for different purposes. For example, large area models like the one on the left can be used to assess habitat characteristics, whereas on the right, colony scale models can be used for more fine scale growth measurements. Similarly, depending on the purpose, 2D photogrammetry products can be used to examine large spatial trends using imaging techniques such as vessel-mounted imaging rigs, or close-range spatial ecology could be examined using diver rigs. So photogrammetry can be used to assess many ecological metrics related to reef resilience, recovery, and function. For example, in this diagram by Guozzo, we can see spatial, demographic, and environmental factors that all influence recovery of reefs. So nearly all of them can be directly measured using photogrammetry. Furthermore, if you saw Manu's talk yesterday about vital indicators of reef health, we can see that most reef metrics that require monitoring can also be quantified using photogrammetry. This can dramatically increase in-field data efficiency relative to using different methods to measure each metric individually. So the methods by which these different data are extracted from 2D and 3D photogrammetry outputs are varied and use a wide range of different software and platforms. The techniques that this data can be extracted using can range from using AI integrated classifiers to detect, segment, and identify coral taxa, such as in a platform like TagLab. You could examine spatial clustering and distribution of taxa from 2D models in ArcGIS. We could extract 3D habitat complexity metrics such as rugosity from 3D models using Python codes. Or we could measure 3D or 2D growth of coral colonies using these or other platforms. We can also compare all of these data across time to inform temporal patterns and trajectories. So as part of the EcoRRAP sub-program of RRAP, we've been designing, testing and applying a time series photogrammetry pipeline to examine many of the factors influencing reef recovery and resilience in order to better inform on the what, where, why and how of reef restoration. So this project spans over 350 sites on 17 reefs in clusters spanning the Torres Strait to the Southern Great Barrier Reef, at inshore and offshore sites, and in different reef habitats and depths. So this project has also been running for 4 years. So each zone shown here is approximately 1,000 square meters in size and is imaged using high resolution DSLR techniques in each of the plots shown, and GoPro techniques for the larger spatial extent. So the current outputs of this ongoing project include the production of a series of manuals and standard operating procedures describing the techniques used. These are designed to enable other users to replicate or adapt these techniques for ecological monitoring and research. The first of these manuals relates to data collection techniques and is available on the AIMS website or through this QR code, while the other two relating to model processing and data extraction are due to be published in the upcoming months. In addition to these manuals, Python scripts and AI classifiers will be made open source and available to all users for their own applications as well. All data and metadata created in this project is available on request and can be accessed through the AIMS data portal. And we've also uploaded a low quality version of all of our 3D models to view and download on Sketchfab. So please contact myself or Renata if you're interested in collaborating or accessing any of these data sets. We're also planning to publish some data papers to make these sets more available and accessible to a wide range of users. So now the fun really begins. We have been collecting data for 4 years, and now our team is currently up to their necks in analysing and writing up all the data. So if you caught Renata's talk yesterday, you might have seen a sneak peek at some of the first large-scale pattern analyses of benthic community composition and distribution across the Torres Strait and Great Barrier Reef. But watch this space for upcoming publications regarding a range of spatio-temporal trends in reef metrics across the Torres Strait and GBR, and an examination of how they relate to other essential functions influencing reef health, resilience and recovery. Now, if these aims weren't ambitious enough, I'd also like to share a few examples of some of the other projects and photogrammetry applications that our team and collaborators have been working on to give you a bit of an idea about some other examples of how these diverse tools can be applied. So I'm sure you're all aware of the recent declaration of a mass global bleaching event that's currently unfolding on our reefs. So while photography is a fundamental tool for assessing bleaching, we've currently been developing tools to apply photogrammetry to facilitate assessments of bleaching at larger spatial scales and over larger colony numbers. So an example of this is Mariana's presentation on Tuesday, which showed how the use of photogrammetry in the 2022 Central Mass Bleaching event could enable the extraction of large volumes of data relating to taxa identification, bleaching severity and extent, multiple colony size measurements across large spatial scales with minimum in-water input. Furthermore, the use of photogrammetry enabled the analyses to be adaptive to trends observed. For example, this allowed us to collect data on taxa that were not anticipated to be assessed, but displayed unexpected responses. So over the last few weeks, our team has also been out conducting photogrammetry surveys of over 24,000 square meters of reef across the Torres Strait and Great Barrier Reef. So in conjunction with this, we imaged over 2,000 colonies and assessed them for bleaching severity and in-water extent, with the intent of training an AI model to automatically quantify bleaching from the imagery. So using time series photogrammetry techniques, it also allows us to provide powerful tools for communication and sharing information about the impacts of disturbance events with others. So here you can see two slider comparisons of inshore reefs in the Central Palm Island group and the Southern Keppel group prior to and after the recent bleaching event. QR codes for these interactive sliders are available here, as well as a conversation topic in which they were published yesterday. So photogrammetry techniques are also being integrated with AI and automation technologies at an increasing rate. This includes developing autonomous vessels and processing pipelines to automate image collection and model creation over large spatial scales, as well as the incorporation of new AI image segmentation and classification tools to automate the extraction of data from 100% of images captured to increase the available information by orders of magnitude relative to traditional point subsampling methods. So in summary, I hope I've helped increase your understanding of the many ways that photogrammetry can be used as a tool to assess key reef metrics to inform on reef resilience and restoration, and maybe even spark some ideas about novel research questions or applications in your area of interest. So I'd like to thank you all for your time, and I'd like to acknowledge the huge amount of work and the large number of people who've contributed to this project and the work we do. Please feel free to contact myself or Renata if you'd like to collaborate or access any of these data sets mentioned, or to chat about how you might want to apply these technologies to achieve your goals. Thank you and enjoy the last day of your conference, and thank you to Renata for fielding any of your questions.
Hi everyone, I'm Maureen and I'm part of that EcoRRAP team, so feel free to ask me any question and I'll try my best to answer.
I do have a question. So they were talking about scaling up and using those robotics and kind of trying to create an automated system. How far away is that?
I have no idea.
Okay.
It's
wonderful data and it's fantastic,
yeah,
and it would great to be able to have that at scale. But it's a lot of work, and I know how much work it is as someone who works in similar areas. To be able to scale that up is going to be an amazing effort.
Yeah, it's more the work of Reef Scan and Scott Bainbridge, so he would be the best person to contact. And yeah, they're really scaling up and so building these orthomosaics, but for even bigger scale. So yeah.
Awesome.
Hi. Do you happen to know what the size of each of those models are, and maybe talk a little bit about your data storage plans and how much space that takes over time?
Petabytes. So yeah, we're fortunate enough to have AIM servers to store all of our data and multiple backups. And so the size of each model is 12 by 6 meters, and the size of the outputs depends on what the output is. So obviously the 3D model are quite heavy. So yeah, that's something that for sure needs to be accounted for before collecting all these data, because yeah, you have the raw images and then the different outputs at the different steps.
Well, it's wonderful, innovative research. Thank you, Maria, for answering those.
Thank you.
And